Have you ever looked up at the night sky and wondered about the oldest things you can see? We think of stars as ancient, but what if I told you there is a star out there that seems to be older than the universe itself? It sounds impossible, right? Like finding a photograph of your grandparents before they were even born. But that's exactly the puzzle astronomers are facing with a star nicknamed Methuselah. This isn't just any star. Its official name is HD 140,283, and it's located about 200 light years away from us. It's one of the oldest stars we've ever discovered. But here's the kicker. Early calculations suggested it was around 16 billion years old. Now, if you know anything about cosmology, you know the Big Bang, the event that created our universe, happened about 13.8 billion years ago. So, how can a star be 2 billion years older than the very universe it lives in? This isn't just a small error. It's a cosmic paradox that could fundamentally challenge our understanding of everything. Let's dive into how astronomers even figure out a star's age. It's a fascinating bit of cosmic detective work. One of the main clues is the star's composition. Stars are like giant recycling plants. The very first stars in the universe were made almost entirely of hydrogen and helium, the lightest elements forged in the Big Bang. Over billions of years, these stars cooked up heavier elements in their fiery cores through nuclear fusion. When these stars died, they exploded, scattering these new, heavier elements, what astronomers call metals, across the cosmos. Subsequent generations of stars, like our Sun, formed from this enriched gas and dust, so they have a higher concentration of metals. The Methuselah star is what we call metal poor. It has incredibly low levels of elements heavier than hydrogen and helium. This tells us it must be a very ancient star, belonging to one of the earliest generations, known as population to stars. Its composition is a clear signpost pointing to a very distant past, long before stars like our Sun even existed. Another key to a star's age is its brightness, or luminosity. As a main sequence star like our Sun gets older, its core gradually converts hydrogen into helium. This process makes the core denser and hotter, which in turn makes the star shine brighter. For a star like Methuselah, which is now leaving the main sequence and becoming a subjet, its brightness is a direct indicator of how much fuel it has burned through. By measuring its luminosity very precisely, astronomers can estimate its age. The brighter it is for its mass, the older it must be. And Methuselah is unusually bright for its low mass, which is another reason it was initially calculated to be so ancient. But measuring these things isn't easy. To get an accurate age, we need to know exactly how far away the star is. Distance is crucial because a star that is intrinsically faint but close can look just as bright as a star that is intrinsically luminous but far away. For years, the distance to Methuselah was uncertain, leading to a wide range of age estimates. This is where the European Space Agency's Gaia mission came in. Gaia is a space observatory dedicated to creating the most precise 3D map of our galaxy ever. By measuring the parallax of stars, the tiny apparent shift in their position as Earth orbits the Sun, Gaia can calculate their distances with unprecedented accuracy. With this new, more precise distance measurement, astronomers were able to recalculate Methuselah's age. The initial mind-boggling figure of 16 billion years started to shrink. The new calculations brought the age down to around 14.5 billion years. Okay, that's better. But it's still older than the universe's age of 13.8 billion years. We're still left with a paradox. So, what's going on? Is our understanding of the Big Bang wrong? Well, probably not. Scientists are very cautious before throwing out a well-established theory like the Big Bang, which is supported by mountains of evidence, from the cosmic microwave background radiation to the expansion of the universe. Instead, they look for uncertainties in their measurements and models, and there are several. One of the biggest uncertainties lies in the star's own physics. Our models of how stars evolve are incredibly sophisticated, but they're not perfect. For example, the rate at which elements like helium diffuse downwards into the star's core can affect how it burns its fuel and how bright it appears. Another factor is the amount of oxygen in the star. Methuselah has a surprisingly high oxygen to iron ratio. Oxygen is a key element in the fusion process that powers a star. A higher oxygen content could mean the star burned its fuel more efficiently, making it look older than it actually is. When astronomers adjusted their models to account for these factors and combined them with the new Gaia data, the age of Methuselah came down even further. The most recent estimates place its age at about 14.27 billion years, plus or minus about 0.8 billion years. That plus or minus is the key. It's the margin of error. Suddenly, the star's age overlaps with the age of the universe. The lower end of its estimated age, around 13.5 billion years, fits comfortably within the 13.8 billion year age of the cosmos. The paradox, it seems, might just be resolved by the uncertainties in our own measurements. But let's play devil's advocate for a moment. What if it's not the star's age that's wrong? What if it's the universe's age? The age of the universe is calculated based on the rate at which it's expanding, a value known as the Hubble constant. But here's another cosmic mystery. Different methods of measuring the Hubble constant are giving slightly different results. Measurements of the early universe, using the cosmic microwave background, give one value. Measurements of the nearby modern universe, using things like supernova, give a slightly higher value. This discrepancy, known as the Hubble tension, is one of the biggest problems in cosmology today. If the expansion rate is actually faster than we thought, it would mean the universe reached its current size more quickly, making it younger. But if the expansion rate was different in the past, it could change our calculation of the universe's age. If the universe were, say, just a little older than 13.8 billion years, then Methuselah's age wouldn't be a problem at all. So, this one humble star, HD 14283, sits at the intersection of two of the biggest puzzles in modern astronomy, the evolution of stars and the expansion history of the entire universe. It acts as a powerful check on our cosmic models. For now, most astronomers believe that the Methuselah problem can be explained by refining our understanding of stellar physics and shrinking the error bars on our measurements. It's a testament to the scientific process an anomaly appears. It challenges our theories, and it pushes us to make more precise measurements and build better models. The star that seemed to shatter the Big Bang didn't actually break cosmology. Instead, it forced us to sharpen our tools and deepen our understanding. It's a reminder that in science, a paradox is often not a sign that our theories are wrong, but an opportunity to make them more accurate. The universe is full of these wonderful puzzles, and Methuselah is one of its most fascinating. It's not older than time, but it is one of the oldest relics we've ever seen, a direct link to the dawn of the cosmos, when the first stars were just beginning to light up the darkness. What do you think? Is it just a measurement error, or could this ancient star be pointing to a flaw in our understanding of the universe's age? Let me know your thoughts in the comments below. Thanks for watching, and if you enjoyed this journey to the edge of time, don't forget to like this video and subscribe for more deep dives into the mysteries of the cosmos.